In differential equations, Euler's equations are equations in the form where you have, it's a second order differential equations when you have the coefficients of y double prime is t squared, and the coefficients of y prime is alpha t, and the coefficients of y is a constant beta. Keep in mind that alpha and beta are constants. T and t squared are the functions of t, and you have a second order differential equation. So if an equation is in this form, then it's called Euler's equations. And we'll discover how to solve these types of equations. So the first thing I want to do is we want to introduce a new variable. I call it x equals to, I said x equals to natural log of x. So, x equals to the natural log of t. So if x is equals to natural log of t, then we know that dx dt is 1 over t, right? So that's one information that we know from this equation. What else do we know? So that means you could say that dt is the same as x times dx, right? T times dx, actually. Okay. All right, so we're going to leave it there for now, and we will use this later. Now, we want to figure from this new variable here, we want to figure what is dy dt, right, in terms of x. So dy dt, we're wondering what is dy dt in terms of x, because we do have to solve these equations in terms of y. So dy dt equals to dy dx multiplied to dx dt. Okay. What is dx dt, which is founded here, which is 1 over t. All right, we're going to leave it there for now. Now go to the second derivative, d squared y and dt squared. So the second derivative of y in terms of t equals to the derivative of the first derivative, which is dy over dx times 1 over t. All right. Well, at this point, we're gonna use the product rule to find this derivative. So we'll have dy d squared y dt dx, okay, and multiply to 1 over t plus just dy dx, multiply by negative 1 over t squared. All right. So now we're going to use this information here to solve these terms here. So it turns out that if dt over dt equals to t dx, then dt, I will replace dt by t times dx. I will get d squared where, so dx t 1 over t plus dy dx negative 1 over t squared. All right, so then you can see that it's going to be d squared y and dx squared 1 over t squared plus dy over dx multiplied by negative 1 over t squared. All right, so now we have dy dt and d squared y dt squared in terms of dx, dy dx, and in terms of t functions. We're going to replace these functions, these informations into our original functions to see what we get. We will get t squared, right? d squared y dt squared is going to be this term plus beta I think it uses alpha t, and dy dt, which is dy dx times 1 over t plus c beta y equals to 0. So this is the original equation where I replaced dy dt in terms of dy dx and functions of t. All right, now I can just simplify this equation a little bit. So I get this gonna gone, right? So I will have, oh, I'm missing this part right here. So I should have more than just this. First go back here. You have t squared and d squared y dx squared 1 over t squared plus dy dx times negative 1 over t squared. Okay, so again, this is d squared y dt squared. This is dy dt. All right, and then now I can just simplify this a little bit. So this will be gone. So what I have is d squared y dx squared. I have dy dx, and I can combine the dy dx together here. This is gone. So what I have is alpha. This is gone out here, minus 1 dy dx and beta y equals to 0. Now I have a new equation, still second order differential equations, functions of y, but in terms of x. And my equation now has only constant coefficients. These are constants. Since alpha and beta are constants, so now I have, this is called second order, right? Okay, differential equations with constants, coefficients. Okay, and I know how to solve for second order differential equation with constant coefficients. And then I can solve for x. Once I have x, I can solve for y, right? Because if x equals to natural log of t, then I can solve for y in terms of x. And once I have the function of y in terms of x, I just replace x by natural log of t. So if you have y in terms of x, then you can replace this. It's the same as y of natural log of t. So now you have a function of y in terms of t. Okay. So to summarize this, this method on how to solve Euler's equations, first you want to introduce a new variable x equals to natural log of t, and then you transform from Euler's equations into an equations that in terms of y and x instead of y and t. So you will have, as you notice this, you will have a function, a differential equations dy dx, right, instead of dy dt, and so on and so forth. So you came up with it with this new equation, and then you know how to come up with this new equation once you identify alpha and beta. And once you have this new equation, you can solve for y in terms of x. Okay. And you can check whether these two functions form a fundamental set of solutions, and then you can substitute x by natural log of t to get your final answers, two functions of your final answers. So recognize Euler's equations, transform it into these equations, solve for y in terms of x, and replace x by L and T to get your final solutions. All right, let's do an example. Here we have an Euler equations, right? You have t squared, you have negative 4t, you have negative 6. Okay, so I know that my alpha, so I want to make sure that I know what I'm doing. So alpha is negative 4 and beta is negative 6. And I let x equals to natural log of t, right? I consider the new equations. Which is y squared dy d squared y dx squared plus alpha minus 1, which is negative 4 minus 1 dy dx plus beta, and beta is negative 6, so it's negative 6 y equals to 0. All right, so now I have a functions d squared y dx squared minus 5 dy dx minus 6y equals to 0. So this is a differential equations with constant coefficients. I will try to solve this equation by finding the characteristic polynomial. And remember, we have r squared minus 5r minus 6 equals to 0 is my characteristic polynomial, and I can solve for this. Should be solve this equation using factoring. Let's just try to factor this quadratic equation. As you can see, negative 6 times 1 is negative 6. Negative 6 plus 1 is negative 5. So then I have r equals 6 and r equals to negative 1. Okay. And then from previous lecture, I know that my solution will be y equals to c1 e to the rt, which is 6t, right? Plus c2 e to the negative t. All right. Well, this is my equations here. This is my solutions here. You have, if you separate it out, you know that this is y1 and this is y2, and the solution is a linear combinations of y1 and y2. Okay. All right. So now, if you want to know whether these two solutions, y1 and y2, are forming a fundamental theorem of fundamental solution sets, you can find the Kronskian of these two functions. So the Kronskian of e to the 6t and e to the negative t should be equals to, so again, this is y1. So then y1 prime would be e to the 60, 6 e to the 60 and then y2 will be e to the negative t, so y2 prime is negative e to the negative t. And the Kronskian should be e6t times negative e to the negative t minus 6e to the 6t times e to the negative t. Okay, and then you will get negative e to the 5t minus 6 e to the 5t. So then the answer is -7 e to the 5t. And -7 e to 5t, as you know, that is always different than 0 for t is positive. Okay, so we know that y1 and y2 are forming a fundamental set of solutions to the differential equation, and then I can conclude that the solutions for this equations is y equals to c1 e to the 6t, this should be sx. Remember, we're solving the equations, right, in terms of x. So then you want to have, this is 6, instead of x, you have ln t, okay, plus c2 e to the negative, instead of x, you have ln t. Okay. And then you can simplify it. Actually, it's going to be c1 e to the ln t to the 6, so t to the 6, plus c2 e to the t to the -1, c2 1 over t. So this is y in terms of t, and is the solutions, general solutions to the differential equations. Here we go. You have an example of how to solve an Euler's equations. Keep in mind that there's several mistakes that we could make along the way, right? First, you have to identify alpha and beta. Let's remember alpha is -4 here and beta is -6 here. Second, you can transforming this differential equations into a new differential equations in terms of y and x, right? And this is a constant coefficient equation, so we know how to solve for it by come up with the characteristic polynomial, finding the roots, and then you know that these roots will form solutions, and there's two solutions here. And keep in mind that this is going to be x. Remember the earlier, I forgot that I was solving for y in terms of x instead of y in terms of t, so make sure that you know these are x, and you can find the Gronskians of the two equations, two solutions, two functions, to make sure that they're forming a fundamental set of solutions for the differential equation. If the result is different than 0, then we go ahead and use those solutions. And then the last step is we conclude that the solutions is we replace x by ln t. So earlier we found that this is 6x, and we set x equals to ln t, so we have to replace x by ln t to come up with our final solutions. And you can simplify this by e to the ln t to the 6, so t to the 6, and e to the ln t to the -1, 1 over t. That this should be your general solutions. Here we go, Euler's equation. Second order differential equations with non-constant coefficients. But if in this form, then we can solve these types of equations.